So this video is the second of two little extra lessons that go on the end of Chapter 1 for Physics 12. And in this one here, we're going to look at something that I like to call checks and arrows. It's just a quick little way of trying to figure out the answer to some what we call principles of physics questions, where things are changing and we're trying to figure out what the answer is going to be. And it works off of this booklet right here. This is a booklet where the first two examples look almost identical. It's about an airplane accelerating from rest. In this first example, we're told that it accelerates at 3.125 meters per second squared. And then in the second example, it's the same story, but they don't tell you the acceleration. So let's look at the first one up at the top of the page there. It says at the end of the runway, right at the end of the runway, the final velocity is 64 meters per second. And then it says the same airplane now accelerates down a runway that is twice as long, and assuming the same acceleration as before, what will the final velocity be? And first glance you might think, oh, okay, well, with one runway got to 64, maybe this one's going to be 128, right? We're going to see. And almost all of these questions that we're going to do end up with this sort of situation where there are two trials going on, right? So you've got, trial number one going on here. And it worked. It's fine. The answer was 64 meters per second. And then here's the same airplane now on trial 2. Let me make this a little easier to see here. Okay, so we know the acceleration is 3.125 meters per second squared, but we don't know the length of the runway, either the short one or the long one. So here's one method to deal with this question. It's not the one that we're going to use for kind of our standard checks and arrows practice, though, but we'll go through it because some people try this. They say, well, why don't I use the information that's there to try to find the length of the runway? Why don't we go and find D, right? Like, how big is this original runway? Well, they're talking about final velocities. They mention the initial is at rest. There's acceleration, there's a displacement, but there's no talk about time. So a great equation to jump to would be Vf squared minus Vi squared is equal to 2AD. And we can actually use this pretty quickly to find out how long the runway is, right? We get up to a speed of 64, initial was 0, to, hey, thank you for telling me the acceleration 3.125, and then we're looking for D. And so without too much trouble, I can use that acceleration that's just at the top of your screen there on the left, and I can find that this first runway is 655.36 meters, somewhere in there. Okay, great. Now let's reuse that information. The second runway is twice as long. Okay, so let's reuse the info. It was great that we were able to find that original displacement. So twice that, 2D, would be double that 655. Okay, it's going to be 2 times the 655 number. And what we can see is we can know that the second runway is 1,310 meters, 0.72. And now we can go and recalculate. Okay, so final velocity squared minus 0 squared is equal to 2 times that acceleration. We were told it wasn't going to change, and then 1310.72. All right, things are awesome. We're done. Final velocity ends up being, surprisingly, not 128. Actually, it's not all that surprising. But it is less than that 128. It's 90.5. So actually, the correct answer, I guess, is C. If you were thinking it should be 128, it's got twice as much room to go. You have to realize that the second half of that trial 2, the second half of the runway, is actually going to happen very, very quickly because the plane's already got an initial velocity as it goes into that second half. So it actually exhausts the second half of the runway in a fairly quick time compared to the first half. So it doesn't have much more time to accelerate. That's why it only gets up to 90.5 instead of 128. Well, in any case, I don't like this method because we needed to know that the acceleration for this thing was 3.125. What if they didn't tell you that 3.125? You wouldn't have been able to find the displacement so that you could double it, so that you could reuse the information. And that's what's going on now in example 2. It is the exact same story. Look, let's be honest, it has the same answer, 91 meters per second. But how can we go about finding that answer if they don't actually tell us the acceleration? and the displacement, right? So this story for both trials, it's way more interesting because we're missing A and D. But there's a way out, okay? What I like to call checks and arrows. So here's a kind of a crash course on how they work. First thing you do is you find the equation that deals with your story. Well, we want the equation that's talking about kinematics but doesn't have time. So that would be this one here. In fact, we used it up at the top of the page. And we were successful with it because we had the acceleration. Well, tidy it up if you can. I know that the initial velocity is 0, so okay, gone. Don't need to have that. And I can get to here, Vf squared is equal to 2AD. Now my advice is, until you're really experienced with these checks and arrows questions, take the variable that you're looking for, that you're being asked about, and isolate it. We're being asked to make a comment on Vf, and right now it's Vf squared, so I'm going to go and take a square root. And don't hold back on the size of your root symbol here, because we're going to be packing some notes in underneath this symbol. Okay, inside there is a 2 and an A and a D. All right. Now, somebody has gone and done this calculation for the first airplane on the first runway, and they got that answer of 64. Trial number 1 is finished, and it was very successful. It worked great. Now we're trying to do trial number 2, and what you want to do is compare and contrast those two trials. How are they the same, and how are they different? Well, in both trials, when the person was doing the calculation to find out that final velocity, and they were calculating that 2AD, in both trials, that big giant 2 was sitting there, right here. So what I like to do is put a check mark by things that don't change. So that 2 is not going to affect this answer in the sense that it was present in both trials. Okay, it was present in, trial A over here. There's trial A, and here's trial B with that airplane. In both trials, that 2 was there. It's not going to change the math. The acceleration, also the same. So let's put a check mark on it. But in trial B, if we compare B back to A, the displacement is larger. So let's put an arrow on that and say, hey, that's going up. And there are many times when we actually know by what factor it goes up. So I'm going to put a little times 2. Okay, that D was twice as big in trial B as it was in trial A. Okay, well, how does that affect that right-hand side? Well, there's this product of 3 things there, right? I'm just going to circle that. I think math people would call this the radicand, right? The number inside the radical. So that radicand, that green blob, is going to grow. It's definitely going to go up. Now, the 2 didn't change, the A didn't change, but the D doubled. That makes that green number go up by a factor of 2. Okay, so there's now a factor of 2 showing up underneath this root sign, this square root sign. That's going to make that whole right-hand side larger, but not doubly. It's just going to be root 2 times larger than what we had before. So sure, I'm going to say, hey, the right-hand side grows, so does the left-hand side. This has to go up, but it goes up by root 2. I can now figure out really easily what that final velocity is. The final velocity will be the old final velocity of 64, but it will be root 2 times larger. That's a really, really quick calculation, right? In terms of how much you need your calculator for. 64 times that root 2, 90.5, done. So we're going to call that game checks and arrows. There's kind of a more elegant, official way to do it, but this is going to work just fine for everything we're doing. We're just going to write down the equation that's important, and then we're going to clean it up as much as we can, and then we'll just put checks on things that aren't changing and arrows on things that are. So let's kind of make this a little bit more official. For these kind of like, hey, write down your thoughts questions, they almost look like paragraph questions. Maybe if a teacher or a professor is giving you a test, they might give you some like lined space to write down your comments. So we'll call them paragraph questions with air quotes around them. Don't feel you need to give a paragraph answer. In fact, please don't. Write down some math, write down the physics that's happening, and then make some point form comments on what you see happening with that math. If it's a question about forces, consider drawing a free body diagram. Think about what physics equations involved. We just did one that was Vf squared minus Vi squared equals 2AD. And until you're really good at it, isolate the variable that you're interested in, get it by itself, and then we can do checks and arrows. Check the variables that are constant. Use arrows to show variables that are going up and down. And then you do have to describe in words, it can be point form, what you mean by those checks and arrows. Assume people don't have any idea where you're going with your checks and arrows as you draw them. So let's try a couple more here. Example number 3. Got a race car. Race car starts from rest and accelerates at a constant acceleration for a short period of time, and it covers a displacement of 255 meters. Okay, it's done. Trial number 1's over. The car managed to go 255 meters. That was its displacement. In a second trial, the acceleration is, it's different, 3 times less than the original, but the car accelerates for a time period that is twice as long. Okay, well, this is an interesting story. There's lots going on here. People are talking about the acceleration of the car. It's not a force, so I'll just kind of draw it out there. It's not really a free body diagram. Not worried about that yet. There's definitely some sort of displacement that's happening for this car, right? It goes down the track, right? They're actually kind of focused on how far it goes. What else have we got? And there's a time, right? Like how much time is it going to take to get to the end of the track, right? So at this point here, suddenly the stopwatch says, stop, right? Can't go any farther. Okay, so we need an equation that's going to bring those issues together, because they're asking us, do you think the displacement in the second trial is less, the same, or more than before? And then we've got to justify our answer. Well, kinematically, I think we'd be best to go with VIT plus 1/2 AT squared. It deals with all the things that they're talking about, and it doesn't deal with final velocity. Nobody seems to want to talk about that. Okay, tidying it up. Well, the car started from rest, so why are we looking at this? Throw that away. That's gone. And then we end up with just this. The displacement is equal to a 1/2, and then an A, and then a T that's getting squared. You don't have to put brackets around it, but I just want to for a moment. Okay, let's talk about how trial 2 is maybe a little bit different than trial 1. In both trials, the 1/2 is there. That's not changing the math. Okay, that is in both calculations. But in trial 2, they've said the acceleration shall be less. In fact, they said less by a factor of 3. So if you know information's about the factor, throw it in. Now, people might say it's 3 times less, or they might say it's 1/3 as big. Yeah, sure, all the same thing. The time, they said, would be twice as much. So just the value for t goes up by a factor of 2. Well, that's getting squared. It's like having 2 t's side by side, and they're both growing by a factor of 2. So this entire quadratic little factor in there, that green blob, that's going to go up by 2 squared. That's going to go up by a factor of 4. Okay, well, what's going to happen to the overall displacement? We've actually got competing effects here. The acceleration is trying to make that right-hand side 3 times smaller, but the time is trying to make the displacement 4 times bigger. And you can just multiply those issues together. So it's looking to me like that right-hand side and the left-hand side, it's an equality, right? It's going to grow by a factor of 4/3. It's going to be a little bit bigger than before. Okay, great. Let's go and figure out exactly how far this thing's going to go now. Right? So that displacement, it's going to be the old displacement, 255, and then we'll just multiply it by 4/3. So actually the displacement, the new displacement for this car is going to be 340 meters. Done. Definitely more than before, even though the acceleration is less. Right? That time being quadratic was a little bit stronger effect there. It caused that displacement to be bigger. Okay, this is working pretty good. Let's go and try another one out. Rocket that starts from rest, accelerates over a short distance at a constant acceleration and reaches a final velocity of 480 meters per second. Okay, great. A second rocket also starts from rest, but accelerates with twice the acceleration for a distance that is 8 times the first rocket. Oh, we've got a few changes going on there. Okay. We have to try to figure out the final velocity of that second rocket. We don't even know anything about the distance the first one went, or the acceleration value. That's okay. We know some information about the changes. For this story that we've got going on here, it's sounding to me like we should maybe go with VF squared minus VI squared is equal to 2AD. Nobody is talking about time. And they're also mentioning that the rockets start from rest, so throw that away. Let's make life simple. And as I try to tidy this up, I end up with VF squared is equal to 2AD. And now what I'm going to do is I'm going to take a square root. Okay, so that VF, it's going to be the square root, I'll leave lots of room here, of 2 times A times D. All of that's in that radicand. Okay, so trial 2 for rocket number 2. When you do that calculation, this 2 will have been there for the first rocket and for the second rocket. There's no change. It doesn't change the math story. So let's just put a check mark on it. But they did say rocket number 2 has a better acceleration. The acceleration they said would be 2 times as big. Okay, good, great. Got some info in there. They also said the displacement would be bigger, actually bigger by a factor of 8. So I've got the A trying to make that radicand 2 times as big, and I've got the D trying to make it 8 times as big. So the whole radicand here, okay, just this green blob, that green blob's going to grow. It grows by a factor of 2, and then by a factor of 8. It's going to grow by a factor of 16. But that green blob is underneath a root. So the actual right-hand side is going to grow by the root of 16. Well, that's just 4. So it looks like that left-hand side also has to grow by 4. Okay, this goes pretty easy. You want to know what that final velocity is for rocket number 2? Just take your first velocity, 480, and we're going to multiply it by that 4, by that root of 16. We're done. Final velocity is 1,920 meters per second. Okay, that's working pretty good. Let's see what the next one entails here. Oh, I got a little warning. Be careful with addition. Turns out it's actually going to be a subtraction, but addition and subtraction are both dangerous, and I want to show you why. A helicopter applies a force FA. They're not going to tell you how much, right? Just some sort of applied force, some sort of tension. Okay, well, let's do this free body diagram. Can always be good to get a free body diagram going. So yeah, okay, great. I've got some sort of FA, fantastic. Upward on a bundle of wood, and the resulting acceleration is 2 meters per second squared. Okay, well, I want to get a nice free body diagram going for this story. I don't even really know what the story is about yet, but a free body diagram is going to be good. There's going to be some weight, mg, because there's a big bundle of wood here, and it's got some mass. Okay, great. Acceleration is 2 meters per second squared. Upward, it's positive. Okay, so that applied force is really intense, better than the gravity force. If on a second attempt, the upward applied force from the helicopter is doubled to 2 FA, what can you say? What statements can you make about the resulting upward acceleration? All right, we need a physics equation relationship that deals with picture with forces and helps us find acceleration. Easy. That's going to be F net equals ma. That's what this whole first chapter has really been about. Okay, so I look at the picture to try to figure out what the net force is. And the picture tells me that the net force is Fa minus mg. And that's making that mass, that bundle of wood, accelerate. All right, what are they asking me for? They're asking me for a comment on the acceleration. Okay, let's do that. Let's take this equation and solve for A. So A would be, as I move that underneath here, it would be Fa minus mg all on top of m, which, by the way, another way to say that, it's the net force. That's what that subtraction is figuring out, all divided by m. Okay, time to play checks and arrows. So what do we know? We know that the FA in trial number 2 will be better than before. They've said it'll actually be twice as good as it was before. Great. The mass, that doesn't change. Same mass. I'm assuming we're on the same planet, so that doesn't change. Okay, so what can we say? Well, I've got this FA that's doubled, and then we're subtracting this mg, but that's constant, the mg. It's not changing at all. Be super careful with additions and subtractions. They kind of mess up our ability to just quickly talk about factors. So if it's just FA that you want to talk about the applied force, great, we can say that it doubled. But for the FA minus the mg, that whole top, that whole F net up here in the numerator, I can look at it and for sure see that it's going to grow, but I don't know by what factor. I know that net force will be better than it was before, but it's not fair for me to say, oh, it's going to double. So whenever you have addition and subtraction in there, any hope of looking at quick little factors is often dashed. But we can still make a comment about the acceleration being better than before, because the mass didn't change, and that numerator did. So the acceleration will grow. I just don't know by what factor. So I would just say, A increases. But sometimes you got to know when to stop talking and not say anything more. And here we just don't know by what factor it increases. Okay, this last one here, kind of a double full page. Actually, grabbed this one from an old provincial exam. Kind of neat looking at the names they gave people. They deliberately made it easy for students. You've got Trial A and Trial B. You've got Art and Bill. Art and Bill both accelerate identical 40 kilogram crates across identical rough surfaces. Okay, there's going to be friction, right? As soon as I see that rough surfaces, I know there's friction. Art exerts an 80 Newton force pushing down at a 30-degree angle with a stick. Bill, also 80 newtons, but up at a 30-degree angle with a cord. Okay. On the bottom of the page here, it says, using principles of physics, explain which one has a better acceleration. Well, let's go for a nice free body diagram. See if we can see what's going on with Art and Bill here. With Art, when he applies that force, I'm going to show it actually down here. It's always nicer to show forces coming out of things. So here's the 80 newtons that Art's going to apply. And that 80 is going to have a couple of components to it. It's going to have a sideways component to it, and it's going to have a vertical component to it. And it's actually pretty quick and easy to find out how big those green little components are. Same 30-degree angle would show up here. And so if you want to talk about Art's FAX and his FAY, easy stuff. FAX would be 80 times the cosine of 30 degrees. And that ends up being 69.3 newtons. Art's FA in the y direction would be 80 times the sine of 30 degrees. That would be 40 newtons. Okay, so we have this 69.3 and this 40. There are more forces though. There's going to be an mg, almost 400, right? Because g is so close to 10, it's actually like 392. There's going to be a normal force. And there's going to be, because of that normal force, some friction. Wow, a lot of forces. So what's the deal with Bill? At first glance you might say, oh, this is going to be identical. This is a tie, right? Let's tear his story apart. He's got an 80 Newton force as well. He's applying it like this. He's also doing it at 30 degrees. And that's really convenient because we don't have to redo the math. That means that his FA in the x direction is also 69.3, and his FA in the y direction is also 40. His box also has some weight to it. There's the mg, 392. And now here's where it gets interesting. Bill's box is going to have a slightly different normal force. Bill's box has Bill helping by holding up at 40, whereas Art was shoving the box down into the ground. His 40 was acting with the 392, So the normal force from the floor had to be really aggressive for Art, but not so much for Bill. Bill's normal force might only be, I don't know, oops, there we go, might only be that big. And a smaller normal force is going to mean a smaller friction force. We have to mention all of those things, if we're being assessed on this. We're not being assessed or tested, whatever you want to call it. We're not being just assessed to see, do you know which box is better? Yeah, okay, you know what? Bill's is. But you're being assessed to see whether or not you can articulate that in a nice, clear physics way. So here's what I would do. I want to mention every single key thing that's happening. Usually I would only talk about trial 2. I'd be talking about Bill and telling you how Bill is a little bit different from Art. For this one, perhaps at the very beginning, I might just kind of clarify that the normal forces have different calculations. For Art, you would actually have an Fn that would equal mg plus that Fay. So his Fn would actually be 392 and another 40, so 432. Whereas for Bill, because he's helping to hold it up by 40 newtons, his Fn is actually mg but reduced by that 40. So his Fn ends up being 352 newtons. Okay. Now, I can even put some checks in there, right? I could say same M, same G, right? Probably worth saying, right? So M, G are constant. You do have to mention that. Okay, you have to mention what all of your little checks mean and your arrows. So what? You've got this Fn that's less for Bill. Well, let's keep focusing on Bill now and kind of wander through the whole rest of the story. So if he's got a smaller Fn, then there's going to be smaller friction. So we have Ff is equal to mu times Fn. Well, it's the identical rough surface, so we can go and put a check mark on the surface coefficient. We should even mention that now. We should say, oh, okay, well, mu is constant. But for Bill, if we're talking about Bill, there's less Fn. Okay, so maybe a little note in here. Bill's Fn is less. Well, that makes the whole right-hand side of that equation smaller. You've got a constant mu and a smaller Fn. So if the right-hand side gets smaller, the left-hand side gets smaller. So we've just verified, we've established in physics court that Ff is smaller. Okay, smaller for Bill. Oh, I always like to talk about what trial 2 is doing compared to trial 1. And you might be thinking, I'm done, right? I want to walk away. Well, now you got to talk about the next big physics issue, and that's F net equals ma. So the net force in that left-right direction would be a battle between the Fax and that force of friction. So you would have Fax minus the force of friction is equal to m times a. If I go and solve for a, which is probably a good plan, I would say, okay, that would be Fax minus the force of friction all on top of the m. Now we've already mentioned over there on that right-hand side that the mass is constant. And we already have mentioned that the force of friction for Bill is smaller. Maybe we should mention that the Fax is the same. Right? So Fax is constant. But that means if you're going to have a constant Fax but a smaller friction force, then this grows. Right? That's F net. Right? So F net is larger, right, for Bill. Okay, well, I've got a numerator that's bigger and a denominator that's identical. So that right-hand side is going to grow. And if the right-hand side grows, so does the left-hand side. Okay, we're done. A is larger. These are all for Bill. So that's the game of checks and arrows. Just carefully work through the physics relationships that are happening. Probably want to isolate the variable that you want to talk about first. Checks on things that are constant, arrows on things that are changing. Sometimes you can put factors in there. Sometimes, like this one, you can't. but you should be describing, like I've done on the right-hand side, what each one of your checks and arrows mean. And we'll be using this checks and arrows method throughout the course. You'll be using it actually throughout, even through like an engineering degree, you'll be doing this kind of analysis all the time. So it's a very powerful tool.